Hello and welcome to lesson 36 of Additional Maths with Mr. Barrow. Today we're going to be looking at something called calculus, specifically the part of calculus called differentiation. Calculus is the study of rates of change, and the way we're going to be approaching it is looking at the rate at which curves change over time. So specifically, the gradient of a curve. Before we do that example there, let's have a look at and discuss how we find the gradient of a curve. So we have done numerical ways of finding the gradient at a point on a curve. We found estimates by drawing tangents with with a ruler and just sort of using our eye to judge about where it should lie and then finding the gradient of that tangent. We've done it by using the gradient of a chord to a point from point P to a point close by, and saying, well, that's an overestimate, so try and get it a point closer. So we've done numerical estimates of the gradient. Today we're going to be looking at finding the exact gradient of the curve at the point P by looking at how we can derive it algebraically. And I'm going to show you a process which derives the algebraic gradient of a curve. But that process isn't needed for every time you try and find the gradient of a curve. Once we've done that process, we'll see that there's a pattern, and then we'll use that pattern to find the gradient of a curve at any point. But firstly, let's have a look at the process. So, before, we've looked at trying to find the estimate for the gradient of the tangent by using gradients of chords from the point P to points close by. So if I did the gradient of the chord PR, that would give me an estimate for the gradient of the tangent, but not a great estimate. If I did the gradient of the chord PQ, that would give me a better estimate because it's closer. So if I brought the points closer and closer to P, I would get better and better estimates of the gradient of that tangent at P. So what we're going to do is we're going to find the gradient of these chords, and we're going to make the distance between those points P and Q get closer and closer and get infinitesimally small. And then we'll find out what that creates in terms of the gradient. Okay, so we'll look at specifically the graph y equals x cubed. And I'm going to find the gradient at a point where the x coordinate is x. If the x coordinate is x, then the y coordinate, well, the function tells me that whatever the x coordinate is, I cube it and I get the y coordinate. So the y coordinate here is x cubed. So at the point P, I have the coordinate x cubed. Okay, well, let's go to a point a little bit further along. So a point Q, okay, a little bit further along. Let's go h along. So this x coordinate is x plus h, so because I've gone h to the right of x. So what's the y coordinate of this point? If the x coordinate is x plus h, the y coordinate is whatever the x coordinate is cubed. So the y coordinate will be x plus h cubed, just using the definition of this specific curve. Okay. So let's find the gradient of the chord PQ. Okay, so the chord PQ, we've got 2 points on it. So the gradient is the change in y divided by the change in x. So if I wanted the gradient of PQ, the change in y is going to be the distance between these two y coordinates. So that will be x plus h cubed minus x cubed, divided by the change in the x coordinates. Well, that's x plus h, take away x, or it's just h, because I can see that the change in the x direction is just this value h. Okay, so let's simplify that. The gradient PQ will be, let's expand the x plus h all cubed by using binomial expansion. You should get x cubed plus 3x squared h plus 3xh squared plus h cubed So that's the expansion of x plus h all cubed, and I've got minus x cubed as well, all divided by h. Okay, so let's simplify the top. And if I simplify the top, I can do the x cubed, take away x cubed, that cancels out. So I'm left with 3x squared h plus 3xh squared plus h cubed all over h. And if I divide everything by h, I just get 3x squared plus 3xh plus h squared. Okay, so that is the gradient of the chord PQ. How does that help us? Well, I know that the gradient of the tangent, so the straight line that touches the curve at the point P, so that line there, the gradient of that tangent will be equal to the gradient of the chord as I move Q closer and closer, as the distance between P and Q becomes 0. So really, the gradient of the tangent is the limit of the gradients of the chords, of the possible chords PQ, as this distance between them becomes nothing. Okay, so how does that work? So I could write down gradient of the curve at P is equal to the limit as h tends to 0. This is the notation we use. We write lim with underneath it h arrow 0. That means the limit of the following thing as h tends towards 0. So it's the limit of this expression, which is the gradient of PQ. So it's the gradient of PQ as h tends to 0 will become the gradient of the curve at P. Okay, so have a think about this. If I have this gradient of PQ, as h turns into 0, what does that turn into? So what is the limit as h tends to 0 of 3x squared plus 3xh plus h squared? Hopefully you'll notice that these two parts, as h tends to 0, those two parts will become 0. Because they both have an h in their expressions, and therefore if we turn h into 0, those expressions turn into 0. So the limit of that entire expression as h becomes 0 is 3x squared. So 3x squared is the gradient of the curve y equals x cubed. That means if I know the x coordinate at any point on the curve y equals x cubed, then I know that the gradient will be equal to 3 times that x coordinate squared. The notation that we use for this is as follows. We say that if y is equal to x cubed, then dy over dx is equal to 3x squared. dy over dx is the change in y over the change in x at an instantaneous moment. So it's the instantaneous change in y over the instantaneous change in x. So basically, because it's changing at every point, the gradient is increasing as we go through the curve, it's changing at every point. If we increase the x coordinate by an infinitesimally small amount, so we're turning h into as small as we can, we're approaching 0, what is the change in y going to be? And if we've got that, then we have the gradient of the curve at that point. So the gradient for x cubed is 3x squared. Now, this leads me to the pattern. If you know a curve's equation, you can find the gradient by using a simple procedure. If y is equal to something times x to the power of something else, then the gradient function is equal to the power comes down and multiplies by it, and then the power drops by 1. So here, the old power was 3, that power dropped by 1 to 2. And the 3 multiplied, the old power multiplied in front of the expression. So we're going to practice that procedure. I will actually, at the end of this video, prove that, why this is always true, because we've only proved it for x cubed, that x cubed differentiates to 3x squared. We haven't shown it that works for any other polynomial, but I will prove that at the end. Okay, but let's use this rule and differentiate some different functions. Okay, so what we're trying to do is we're differentiating in order to find the gradient for each of these functions. Okay, so in this question, I want to find dy by dx for each of these. If y is equal to 7x to the power of 4, what is dy by dx? Well, I know my procedure to differentiate. So finding dy by dx is called differentiating. We take the old power and we multiply the entire expression by that. So 4 times 7x, and then we change the power by dropping it by 1. So 4 becomes 3. So that then becomes 28x cubed. So that is what 7x to the power of 4 differentiates to. Next one. Y equals x plus 5 all squared. Okay, well, this is different. Before we differentiate this, we want to write this out as different expressions with different powers. So we're going to expand this. So this becomes x squared and 10x and 25. Now I'm going to use my procedure to differentiate each of those terms. X squared, the squared has a power of 2. That's going to multiply the entire expression there. So that becomes 2 times x. And then the 2 drops by 1 to 1. Next, 10x is 10x to the power of 1. So that becomes the 1 multiplies by the entire expression. So it's one lot of 10. Then x to the power of, and then the 1 drops by 1 to 0. And the last one, 25, well, 25 is 25x to the power of 0. So if we multiply the entire expression by that power, we get 0 multiplied by 25x to the power of negative 1, because the 0 drops by 1 to negative 1. Now let's simplify that. 2x to the power of 1 is just 2x. 1 times 10x to the power of 0. Well, x to the power of anything to the power of 0 is 1. So it's 1 times 10 times 1. So it's just 10. And then the last bit, 0 times 25x to the minus 1. Well, we will multiply by 0, so you're going to get 0. So that won't have anything that I need to write down. So if I want to differentiate x squared plus 10x plus 25, I get, so x squared plus 10x plus 25, I get 2x from the x squared, I get 10 from the 10x, and I get nothing from the 25. So that will always happen when you have a constant, when you differentiate a constant, so the plus 25, it'll become nothing. That'll always happen when you're differentiating a constant. When you have a power of 1 and you differentiate it, you just get left with the coefficient in front of it. Okay, let's see if you can practice this with your own one. So I want you to find the gradient function for each of these. First one, y equals 9x to the power of 5. And then the second one, y equals x minus 3 all squared. So pause the video, have a go, differentiate those two. So what you should get in this first one, dy by dx, is 45 multiplied by x to the power of 4. Because the 5 has come in front and multiplied by the 9, the 5 is dropped by 1 to 4. And the second one, you expand out first. So y is equal to x squared minus 6x plus 9. Then differentiating, the x squared becomes 2x, minus 6x becomes minus 6, and the 9 becomes nothing. So it's 2x minus 6. Okay. Now let's put this into practice and actually find the gradient of a function at a specific point. So here's an example. Find the gradient of the curve y equals 5x squared minus 10x at the coordinate 3, 15. So the way to do this is, firstly, we differentiate. We find dy by dx. If y is 5x squared minus 10x, then dy by dx will equal what? 5x squared will differentiate to 2 times 5, which is 10, x to the power of 1, so it's just 10x. The minus 10x becomes minus 10. Because remember, if you have a power of 1, you're multiplying by 1, so the minus 10 stays as minus 10, and then drops by 1 to 0, so x to the power of 0 is just the number 1. Okay, so you'll just get the coefficient in front when you have anything to the power of, anything times x to the power of 1. So that's what dy by dx is equal to. That then tells us the gradient for any point on the curve. All I need to do is substitute into this function the x-coordinate, and I know the gradient of the curve. So at the coordinate 3, 15, I know that the x-coordinate is 3. So when x is 3, dy by dx is equal to 10 times 3, take away 10. So 30 take away 10, which is 20. So that is the gradient of the curve y equals 5x squared minus 10x at the coordinate 3, 15. So all you need to do is differentiate and then substitute in your x-coordinate, and you've got the gradient. So have a go at this question. Find the gradient of the curve y equals x cubed minus 8x minus 7 at the point minus 2, 1. Pause and have a go. So the answer to this. Firstly, you differentiate. So dy by dx is 3x squared minus 8. The minus 7 will differentiate to nothing. And when x is equal to minus 2, this gradient dy by dx is equal to 3 times minus 2 squared, take away 8. Minus 2 squared is 4. 3 times 4 is 12. So it's 12, take away 8. So the gradient of the curve at that point is equal to 4. Well done if you got that right. Okay, at this point, if you want to just practice, you can go to exercise 14.1, the first exercise in chapter 14. But if you would like to understand why, with the rule that if we have y equals ax to the power of n, that the dy by dx is always equal to n times times x to the power of n minus 1, then have a look at the next bit that I'm going to prove it. So, for your interest, this is not necessary for the additional maths course, and you may be asked to do it at A level, but probably unlikely. Okay, not quite to this level, but it's going to practice your binomial expansion and your algebra. So if you can follow with this, then great. Now, if I have a curve y equals ax to the power of n, if the x-coordinate is x, then the y-coordinate will be ax to the power of n. If the x-coordinate is x plus h, if I go h along, so just a little bit further along from x, the y-coordinate will be a times that x-coordinate, x plus h, to the power of n. So I've now got two coordinates. The gradient of the curve at this point here, ax to the power of n, will be the limit of the gradient of the chord between these two coordinates as h tends to 0. So for this curve, dy by dx is going to equal the limit as h tends to 0 of the following calculation. The change in y, which is a times x plus h to the power of n, minus a times x to the power of n, all over the change in x, which is just h, as we know. So now I'm going to do some binomial expansion to expand this expression here. So I don't know what the power of n is, but imagine I did know. Okay, so let's expand it using binomial expansion. So I'm going to take a out. I'm going to expand x plus h to the power of n. My first part of the expansion will be x to the power of n. Because if I choose an x from all n brackets, I'll get x to the power of n. My next part of the expansion will be from n brackets, choose one. So choosing the h once and choosing the x n minus 1 times. N choose 1 is just n. In Pascal's triangle, it always goes 1 and then the number of brackets you have, and then it increases beyond. So in the 7th row, when it's bracket to the power of 7, it goes 1, 7, etc. Okay, so the next one, this one here, will be n, which is n choose 1, times by x to the power of n minus 1, times by h to the power of 1. And then that will continue. The next one will be n choose 2, which I'm just going to write as n choose 2, times by x to the power of n minus 2, times by h squared, plus dot dot dot, all the way up to plus h to the power of n, which is the final part of that expansion. Take away ax to the power of n, all over h. So let's tidy that up a little bit. If I multiply all of the bracket by a, I'm going to get ax to the power of n. I'm going to get a times n times x to the power of n minus 1 times h. I'm going to get a times n choose 2 times x to the power of n minus 2 times h squared, plus all the way up to plus a times h to the power of n. And I've also got this minus ax to the power of n as well at the end, all divided by h. If I simplify the top, I get the ax to the power of n cancels with this minus ax to the power of n. So all I'm left with is a times n times x to the n minus 1 h, plus a times n choose 2 times x to the n minus 2 times h squared, plus all the way up to, so the next one will have h cubed, h to the power of 4, h to the power of 5, etc., all the way up to a times h to the power of n, all divided by h. And now all of these parts of the expression, all these parts have an h in them. So I can divide the entire numerator by h. So that then leaves me with the following expression. The first one, if I divide it by h, is left with just a times n times x to the n minus 1. The others all still have an h in them. We've got a times n choose 2 times x to the n minus 2 times h, plus all the way up to, now the last one is now a times h to the power of n minus 1 because I have divided by h. So all of these parts here have an h term in them. So the limit of that expression as h tends to 0 is equal to a times n times x to the power of n minus 1. And there we go. We have proved it. We have proved that ax to the power of n differentiates to an x to the power of n minus 1, which is what we wanted to prove in the first place. So that was just for your interest. That proves the rule that if you have y equal to ax to the power of n, then dy by dx is equal to a times n, so the power comes down and multiplies by it, and then the power drops by 1. So that is y. Okay? If you manage to follow that, superb, well done. This is called differentiation from first principles. And it's a procedure you need to know at A level. It's not a procedure you need to be able to use at additional maths level. You just need to be able to differentiate. You just need to be able to say, okay, I know that I've got y equals 4x to the power of 10 okay, then dy by dx will equal, all right, I think the procedure is times 10 by the 4, so 40, and then drop the 10 by 1 to 9. There we go. That's differentiating. Okay, we don't have to go through this entire procedure of using limits to prove it every time. We can just use the pattern that we found. But it's nice to see where it's all come from, and it's nice to prove it. Okay, so what you should do now, you should practice the procedure of differentiating. So that's exercise 14.1. Okay, and I will see you in the next lesson where we look at finding the equation of the tangent and something called the normal as well to the curve by using our process of differentiation. Okay, off you go and enjoy.